Right now, two different signals are forcing scientists to look again at the fault system beneath Southern California. On July 12th, a magnitude 4.1 earthquake struck just east-southeast of Frazier Park at a depth of roughly 8 miles. About 30 hours later, on July 13th, a magnitude 4.3 earthquake struck west-southwest of Johannesburg in eastern Kern County at a depth of about 5 miles. Neither event caused major damage. Neither one proves that a larger earthquake is coming, but both occurred in a region where several major faults crowd together. Only weeks after a new physics-based study concluded that parts of the San Andreas and San Jacinto systems may now be carrying some of their highest modeled stress levels in the past 1,000 years. The most important change is not that the San Andreas suddenly began racing faster. Scientists have not detected a countdown clock. What changed is their picture of how this fault system can move. A mountain corridor called Cajon Pass may behave like an earthquake gate, sometimes stopping a major rupture, and sometimes allowing it to jump between two dangerous fault systems. Today, we are going to break down exactly what is going on, what the new research actually found, why the recent earthquakes matter and why they may not matter, and what scientists will be watching next. No guessing, no dramatizing, just the facts, the science, and the real stakes. Drop a comment right now. Have you ever personally felt an earthquake in California or anywhere else? Tell me where you were, what moved first, and what the shaking felt like. If you want to be the first to know every time something major happens, subscribe. It is completely free. A thumbs up also helps enormously. Let us go for 5,000 likes on this one, so the algorithm actually shows it to people who need to see it. Now let us get into it. The first event arrived before sunrise on Sunday, July 12th. At 3:38 in the morning Pacific time, instruments in the Southern California seismic network recorded a magnitude 4.1 earthquake about 1 mile east-southeast of Frazier Park. The hypocenter, the point underground where the rupture began, was estimated near 13 kilometers deep, or roughly 8 miles. That is deep enough that there was no surface rupture, but shallow enough for people across parts of Kern and Los Angeles counties to feel a sharp jolt. The U.S. Geological Survey Shake Alert system activated because the earthquake was strong enough and close enough to populated areas for automated warning calculations to begin. A magnitude 2.9 aftershock followed later that morning. In ordinary California terms, this was a light earthquake. Objects may rattle, windows may shake, sleepers may wake. Most well-built structures remain unharmed. The earthquake was important because of location, not destruction. Frazier Park sits near the Big Bend of the San Andreas Fault, where the long northwest-southeast fault changes direction. The Garlock Fault approaches from the east. Smaller mapped and unmapped structures cut through the mountains. Interstate 5 climbs through Cajon Pass nearby, carrying passenger vehicles, freight trucks, fuel, food, and industrial supplies between the Los Angeles Basin and the Central Valley. 30 hours later, another signal appeared. At 9:40 in the morning on Monday, July 13th, a magnitude 4.3 earthquake struck about 11 miles west-southwest of Johannesburg, California. The depth was measured near 7.6 kilometers, or just under 5 miles. More than 1,000 people submitted felt reports. The shaking was noticed across a broad area, but again, there were no immediate reports of serious injuries or major structural damage. Several smaller earthquakes followed around the same cluster. On a map, the two moderate events looked uncomfortably close to famous fault names. That is exactly when online speculation moves faster than seismic waves. Some posts described a chain reaction. Others claimed the San Andreas had awakened. A few treated the two earthquakes as direct proof that a magnitude 7 or larger event was about to follow. Scientists do not have evidence for that conclusion. The July 12th earthquake was near Frazier Park, while the July 13th event was farther northeast near the western Mojave Desert. Seismologists were still refining which smaller structures produced the motion. In a region with many intersecting faults, an epicenter can appear close to a major fault on a two-dimensional map, while the rupture actually occurs on a different plane several miles underground. That distinction matters. The San Andreas is not a single painted line. It is a broad, complicated zone of broken rock connected to neighboring faults, bends, branches, and secondary fractures. A magnitude 4 event can happen near that system without meaning the main San Andreas is beginning a large rupture. Most moderate earthquakes are not foreshocks. They become foreshocks only if a larger earthquake later occurs nearby. Before that happens, they are simply earthquakes. The U.S. Geological Survey has repeatedly emphasized that scientists cannot predict the exact time, place, and magnitude of a major earthquake. Small swarms, animal behavior, radon changes, unusual clouds, and isolated moderate events have all been promoted as warning signs. Most occur without a destructive earthquake following them. That is why the responsible question is not, did these earthquakes announce the big one? The responsible question is, what do these events reveal about a region that was already known to be dangerous? To answer that, we have to go back more than 1 month, more than 1 century, and in some places, more than 1,000 years. On June 10th, researchers led by Earth scientists connected with the University of Hawaii at Manoa published an analysis of the southern San Andreas and San Jacinto fault systems. Their work appeared in the Journal of Geophysical Research, Solid Earth. The team did not drill into the fault and measure a new burst of speed. They did not find a previously unknown crack racing toward Los Angeles. Instead, they built a physics-based computer model designed to reconstruct how tectonic stress accumulated and was released across a complex network over roughly 1 millennium. The researchers combined mapped fault geometry with evidence from prehistoric and historical earthquakes. That evidence came from paleoseismology, the study of earthquakes preserved in the landscape. Scientists trench across fault traces and examine layers of sediment that were offset, buried, folded, or disturbed by earlier ruptures. They date charcoal and organic material with radiocarbon methods. They study tree rings that record sudden tilting, burial, damage, or changes in water supply. They compare those clues with written accounts from the 19th century and modern instrumental observations. Each piece contains uncertainty. A sediment layer may date to a range of years rather than a single day. A historical report may describe damage without precisely locating the rupture. The model does not erase those uncertainties. It tests how different plausible earthquake histories would load and unload the faults through time. When the simulations were carried forward to the present, several fault segments reached modeled stress values at or above the highest levels in the 1,000-year reconstruction. 2 areas drew particular attention: the southern Mojave section of the San Andreas, north of Cajon Pass, and the San Bernardino section of the San Jacinto system, south of the junction. The researchers described the wider system as critically loaded. That phrase sounds like a prediction, but it is not. Critically loaded means the faults have accumulated substantial stress and are capable of producing major earthquakes under the right conditions. It does not tell scientists whether failure will happen tomorrow, next year, or decades from now. The deeper discovery involved Cajon Pass. If you have driven Interstate 15 between the Los Angeles region and the high desert, you have crossed this corridor. Cajon Pass cuts between the San Gabriel and San Bernardino mountains. It is a transportation bottleneck, but underground it is also a structural junction. The San Andreas fault passes through the region. The San Jacinto fault system branches to the southeast. These faults help accommodate the sideways motion between the Pacific Plate and the North American Plate. For years, hazard models have recognized that earthquakes can rupture more than one segment and sometimes more than one fault. The new study tried to explain why some large ruptures stop at Cajon Pass while others may cross it. The model suggests that the junction behaves less like a permanent wall and more like a gate controlled by stress balance. When stress on the 2 fault systems is very different, a rupture may lose the conditions it needs to continue from one system into the other. The gate stays closed. When stress levels on both systems are high and more closely aligned, the rupture may have a better chance of crossing the junction. The gate opens. That is the change scientists detected. Not a sudden new movement visible at the surface, but a different understanding of how a future rupture may choose its path. Historical earthquakes give the model 2 powerful tests. On January 9, 1857, the magnitude 7.9 Fort Tejon earthquake ruptured roughly 225 miles of the San Andreas Fault. Several meters of horizontal slip occurred in places. The shaking lasted between 1 and 3 minutes and was felt across more than 130,000 square miles. California's population was tiny compared with today, and only 2 deaths were widely reported. The rupture propagated along the San Andreas, but stopped near the Cajon Pass region. In the language of the new model, the gate was closed. 45 years earlier, on December 8, 1812, a major earthquake struck the Wrightwood region. Research published before the new study had already argued that the San Andreas and San Jacinto faults may have ruptured together during that event. The earthquake damaged several Spanish missions, and the collapse of a church at Mission San Juan Capistrano killed about 40 people. In that case, Andreas. The rupture appears to have crossed the junction. The gate was open. The contrast between 1812 and 1857 is not just historical trivia, it means the same mountain corridor may control whether the next large earthquake remains on one fault or spreads into a longer, more complicated event. And that changed fast, at least in scientific understanding. For decades, many public discussions treated the southern San Andreas as one main threat and the San Jacinto as another. The newer picture is a network. The danger is not only the strength of one fault, it is the possibility that stress conditions allow multiple sections to participate in the same earthquake. But here's the part nobody should misunderstand. The July 12th and July 13th earthquakes did not prove that the Cajon Pass gate is opening. They occurred north and northeast of the specific San Andreas-San Jacinto junction examined in the study. They do not provide a direct measurement of synchronized stress at depth. They are reminders that the wider system is active, not a trigger certificate for a major rupture. Scientists will examine the focal mechanisms, aftershock patterns, depth distribution, and nearby fault geometry. They may calculate how each event changed stress by a tiny amount on surrounding structures. Those changes can increase stress in one small area and reduce it in another. Usually the effect fades rapidly with distance. A magnitude 4 earthquake releases roughly 1,000 times less energy than a magnitude 6 and about 1 million times less than a magnitude 8. That scale difference is why two-felt earthquakes can be scientifically interesting without being capable of unloading the centuries of accumulated strain on a major fault. To put the San Andreas system in context, imagine two enormous blocks of crust sliding sideways past each other at about the speed your fingernails grow. The Pacific Plate moves generally northwest relative to the North American Plate. Across California, the total plate motion is divided among the San Andreas and many parallel faults. Near Parkfield, portions of the San Andreas can creep at the surface, moving slowly and releasing some strain without large earthquakes. Other sections are locked. Friction holds the rock faces together while the plates continue trying to move. The surrounding crust bends elastically like a wooden ruler pushed from both ends. It can bend for years, decades, and centuries. When the force exceeds the strength of the locked patch, the fault slips suddenly. The stored elastic energy becomes seismic waves. Some waves compress and expand the rock. Others move it side to side or up and down. Surface waves can produce the longest and most damaging motion, especially in sediment-filled basins. Magnitude measures the size of the earthquake at its source. Intensity describes how strongly the ground shakes at a particular location. A magnitude 7.8 earthquake can produce different intensities across a city because distance, soil, basin shape, building type, and rupture direction all matter. Soft sediments can amplify motion. Water-saturated ground can lose strength through liquefaction. Hillsides can fail. Fault displacement can tear across roads and pipelines. Fires can begin when gas lines break or electrical systems fail. The fault does not need to pass under a house for that house to be damaged. In a large earthquake, the most expensive consequences often occur miles from the rupture. Cajon Pass is especially important because geography and infrastructure overlap there. Interstate 15 carries traffic between Southern California, Las Vegas, and the interior West. Rail lines use the corridor. High-voltage transmission systems, communication links, fuel routes, and water infrastructure cross or approach major fault zones throughout Southern California. The Los Angeles region depends on imported water delivered through long aqueduct systems that cross earthquake country. A rupture can offset a pipe by several feet in seconds. Even if the pipe does not split, pumps may lose power, access roads may fail, and repair crews may be blocked by landslides or collapsed bridges. The United States Geological Survey's shakeout scenario modeled a hypothetical magnitude 7.8 earthquake beginning near the Salton Sea and rupturing northward on the southern San Andreas. The scenario was not a prediction. It was a planning exercise built by hundreds of scientists, engineers, emergency managers, and economists. It estimated about 1,800 deaths, roughly 53,000 injuries, and around $213 billion in economic losses in 2008 dollars. The scenario also projected approximately 1,600 fire ignitions, with many becoming too large for a single fire company to control. Water system damage, road congestion, and communication failures would make firefighting harder. Those numbers are not a forecast for the new Cajon Pass model. A joint rupture involving the San Andreas and San Jacinto would follow a different path and produce a different pattern of shaking. The shakeout scenario is useful because it demonstrates how consequences multiply. The earthquake itself may last less than 2 minutes. The infrastructure emergency can last months. Business interruption can spread far beyond California. Ports, warehouses, rail yards, highways, data centers, hospitals, and supply chains are linked. A bridge closure in one pass can redirect thousands of trucks. A water outage can force hospitals and neighborhoods onto limited reserves. A power failure can stop fuel pumps even when fuel remains underground. The difference between a geological event and a disaster is exposure. In 1857, the San Andreas produced one of the largest earthquakes in United States history, but the region held far fewer people and structures. Today, Southern California contains tens of millions of residents. Homes, schools, freeways, warehouses, and industrial facilities cover areas that were ranchland or open desert in the 19th century. Building codes are stronger, but buildings constructed under older standards remain. Some unreinforced masonry structures, brittle concrete buildings, soft-story apartments, and vulnerable industrial systems can perform poorly. Modern towers are engineered to sway, but non-structural damage can still be severe. Ceilings, glass, sprinkler systems, elevators, shelves, laboratory equipment, and interior walls can fail even when the main frame survives. These are not just geological events. They are human experiences. The first seconds are confusion. A low sound may arrive before the strongest motion. Doors swing, lights move, pets run. People try to stand when standing is the wrong instinct. The safest immediate action in most indoor settings is drop, cover, and hold on. Drop before the shaking knocks you down. Cover your head and neck under a sturdy table if one is close. Hold on because the table may move. Do not run outside while bricks, glass, and facade materials may be falling. Do not stand in a doorway unless it is the only available protection in a specific, older structure. Modern doorways are not automatically stronger than the rest of the building. After the motion stops, the emergency changes. Gas may be leaking, water lines may be broken, elevators may be disabled, cell networks may be overloaded, aftershocks can bring down elements weakened by the main shock. Families may be separated across a region where bridges and freeways are closed. That is why preparedness is not mainly about predicting the date. It is about reducing the number of decisions you must make after the ground begins moving. Secure tall furniture to wall studs. Keep heavy objects off high shelves. Know how to shut off gas only if there is evidence of a leak or official instructions. Store water. Keep medications, flashlights, shoes, batteries, and a radio accessible. Choose an out-of-area contact because long-distance messages may work when local calls do not. Expect that emergency services will prioritize fires, collapses, and life-threatening injuries. A household that can function independently for several days gives responders more room to help people in immediate danger. Preparation also creates a striking contrast between places that invest before a disaster and places that improvise afterward. California's modern building codes, retrofits, shake alert system, and public drills exist because earlier earthquakes exposed failures. The 1933 Long Beach earthquake killed more than 100 people and badly damaged schools. That disaster accelerated stronger school construction standards. The 1971 San Fernando earthquake damaged hospitals, freeways, and dams, leading to changes in engineering and emergency planning. The 1989 Loma Prieta earthquake collapsed a section of the Cypress Freeway and killed 63 people. The 1994 Northridge earthquake revealed weaknesses in welded steel connections and caused billions of dollars in losses. Each earthquake changed policy because investigators studied what failed. The June study of Cajon Pass belongs to that same tradition of learning before the next catastrophe, not after it. It tells engineers and planners that a multi-fault rupture may need more attention in scenario design. It tells scientists that the stress relationship between neighboring segments may be as important as the stress on either segment alone. It tells the public that the phrase San Andreas fault is an oversimplification. The real system is a network capable of transferring motion through junctions. But it also tells us something reassuring about science. Researchers are not claiming certainty. They openly describe uncertainty in the earthquake history, model assumptions, and fault behavior. They state that the work does not predict when an earthquake will happen. That caution is not weakness. It is the line between hazard research and fortune-telling. Now we reach the future risk watch. What exactly are scientists checking after the recent earthquakes and the new Cajon Pass study? First, they examine the earthquake catalog. Every event has a time, location, depth, magnitude, and uncertainty. Analysts compare automatic detections with human review. They look for events that were initially merged, missed, or assigned to the wrong depth. Dense networks can detect earthquakes far smaller than people can feel. A cluster may contain hundreds of micro-earthquakes that reveal a line, plane, or branching pattern underground. If those hypocenters align along a known fault, the geometry becomes clearer. If they form a previously unmapped structure, scientists may revise the local model. Second, they study focal mechanisms. A focal mechanism uses the first motion of seismic waves at many stations to estimate how the fault moved. In Southern California, strike-slip motion is common, with blocks sliding horizontally past each other. But reverse, normal, and oblique motion also occur because the fault network bends and compresses. The mechanism can help separate an earthquake on the San Andreas from one on a nearby secondary fault. Third, scientists calculate aftershock probabilities. After a magnitude 4 event, the most likely outcome is a sequence of smaller aftershocks that gradually becomes less frequent. There is always a small chance of a larger event, but that chance usually declines with time if no larger earthquake occurs. This is a forecast, not a prediction. It describes probability across a window, not certainty on a clock. Fourth, geodesists monitor ground deformation using global navigation satellite system stations, satellite radar, strain meters, and creep meters. GPS stations can detect movement of a few millimeters over time. Interferometric radar compares satellite images and maps changes in the distance between the ground and the satellite. After a large earthquake, these methods reveal surface displacement across broad areas. Before an earthquake, slow deformation may show long-term strain accumulation, but scientists have not found a reliable pattern that announces the exact moment of rupture. Fifth, researchers compare stress models. The Cajon Pass study reconstructed 1,000 years using a specific physics-based approach. Other teams will test different assumptions about friction, fault geometry, earthquake dates, slip amounts, and interaction. A strong result should survive those challenges. If small changes in the input completely reverse the conclusion, confidence falls. If many plausible histories still produce unusually high present-day stress and similar gate behavior, confidence rises. This process takes time. It is normal for scientists to disagree about details while agreeing that the region faces serious long-term hazard. Keep an eye on Cajon Pass, but not as a place where a dramatic crack will suddenly appear in advance. The signals are subtler. Researchers will watch whether updated seismicity maps reveal changes in the distribution of small earthquakes. They will monitor creep where instruments exist. They will refine how the San Andreas, San Jacinto, Garlock, and secondary faults connect at depth. They will test whether stress on the southern Mojave and San Bernardino segments remains closely balanced in updated models. They will study how a rupture might turn through bends, jump across gaps, or stop at damaged rock. Computer simulations can run thousands of possible earthquakes, changing the starting point, speed, slip, and direction. The goal is not to find one guaranteed future. The goal is to map the range of credible futures. One credible future is a large earthquake that remains on a single fault and stops at Cajon Pass. Another is a rupture that crosses the gate and involves both the San Andreas and San Jacinto systems. Another begins on a neighboring fault and transfers stress without producing immediate joint rupture. The amount of shaking in Los Angeles, San Bernardino, Riverside, Palm Springs, and the high desert would depend on which future occurs. Rupture direction matters because seismic energy can be focused forward, similar to the way sound energy concentrates ahead of a fast-moving source. If a rupture propagates toward a population center, shaking can be stronger and more coherent than if it moves away. Basin effects matter because the Los Angeles basin can trap and prolong seismic waves. Mountain topography matters because ridges can amplify motion. Soil matters block by block. That is why a single magnitude cannot tell the entire story. The worst case often dominates headlines, but responsible planning focuses on multiple cases. The largest imaginable earthquake is not always the most useful scenario. A magnitude 6.7 beneath a dense urban area can cause more concentrated damage than a larger earthquake farther away. The 1994 Northridge earthquake was magnitude 6.7, yet it killed dozens, injured thousands, damaged freeways, and produced economic losses measured in tens of billions of dollars. It occurred on a blind thrust fault that did not break the surface. The realistic danger in California is not one movie-style crack. It is a portfolio of hazards spread across a network. The new Cajon Pass research adds one more important branch to that portfolio. It suggests that a junction once treated mainly as a boundary between rupture zones may sometimes transmit a rupture from one major system into another. Does that mean the probability of a joint rupture has suddenly doubled? The study did not publish a simple number like that. Does it mean the July earthquakes opened the gate? No. Does it mean authorities should ignore the findings because no date can be predicted? Also, no. Hazard science often changes decisions without predicting an event. Flood maps guide construction even though no one knows the exact day of the next flood. Hurricane codes strengthen roofs before the track is known. Earthquake models guide bridge design, pipeline flexibility, insurance, emergency exercises, and retrofit priorities. The value of the Cajon Pass model is that it challenges planners to consider a rupture path that could connect areas previously analyzed more separately. The most useful next step is not panic. It is verification and preparation. Scientists will compare the model with additional paleoseismic sites. Engineers will ask whether critical lifelines have enough redundancy if multiple corridors fail at the same time. Emergency managers will examine whether shelters, hospitals, fuel distribution, and communication systems can operate when roads through mountain passes are blocked. Residents can take smaller but immediate steps. Move the heavy mirror away from the bed. Strap the water heater. Put a pair of shoes and a flashlight where broken glass cannot cut off access. Download alerts. Learn the earthquake plan at work and at your child's school. Keep copies of important documents and a modest amount of cash because card systems may fail. These actions do not require believing that an earthquake is imminent. They require accepting that California is earthquake country. Now we can close the loop. California's most dangerous fault is not suddenly moving faster in a way that tells scientists the big one is about to happen. The recent magnitude 4.1 and 4.3 earthquakes are not proof of an approaching catastrophe. No scientist can currently predict the exact date, location, and magnitude of a major earthquake. The change is more precise and, in some ways, more important. A new 1,000-year stress model indicates that parts of the southern San Andreas and San Jacinto systems may be at historically high modeled stress, and that Cajon Pass can act as an earthquake gate. When stress is uneven, the junction may stop a rupture. When stress is high and more closely aligned across both systems, it may allow a rupture to pass through and involve more than one fault. That is what scientists detected, a different behavior inside a fault network, not a ticking clock. The biggest fear online is that every small earthquake is a warning siren for an immediate magnitude 8. The evidence does not support that claim, but the smaller, closer danger is real. A moderate earthquake can still damage a vulnerable building. A large earthquake can occur without a clear foreshock. Water, power, roads, and communication can fail even where structures remain standing. The most realistic threat is not a cinematic crack swallowing California. It is a few minutes of violent shaking, followed by days or weeks of disrupted systems. So remember the personal question from the beginning. Have you ever felt an earthquake? Tell us where you were and what happened first. Those experiences help people understand that preparedness is not abstract. If this investigation gave you a clearer picture, help us reach the 5,000 like goal. Subscribe for the next science-based disaster breakdown, and share this with someone who lives in earthquake country. No filler, no guessing, just the facts and the full picture. Let us go. See you in the next one.